What's up, everyone? Welcome back to my channel, and it's finally the year of 2024. Happy New Year. So we're going to finish up the problem that we developed into a couple parts, which is again the very classic ring theory homework problem that you actually found in a lot of abstract algebra textbook. And this time I found it on a textbook that is written in German. So as you can see, the problem is written in German. And you may ask why I did not finish it up and post this video before Christmas, like during Christmas or before Christmas. That is because when I read the problem, I misunderstood the problem and I didn't read the condition carefully. So after I Google Translate, I used Google Translation to translate it, I realized that what the correct meaning of the setup of this part is, which actually makes the problem a lot easier to prove. And if we use the wrong translation that I actually had, in fact, we will not be able to get the results that we need. So what this problem is actually saying that, again, we assume that there is a ring that is not a trivial ring, meaning that besides the additive identity 0, there's other elements in this ring with the condition meets their eigenschaft a squared equals a for all a in R, meaning that for all elements in the ring, it meets the condition that the square of the element is equal to the element itself. In other words, all the elements in this ring are the idempotents. So that is the initial setup for the whole problem. And for this last part here, this is what we want to prove. We want to show that, and here is what the conditions we have. So it says, beweisen Sie, hat R keinen Nullteiler. So it gives R isomorphic to solid 2, meaning that here my wrong translation was thinking that we want to show that this ring has no Teiler, meaning that there is no zero divisor, and which implies or so that this ring is isomorphic to Z2. And again, what is Z2? Z2 is just a ring that contains two elements, 0 and 1, where of course you can think it as the remainders of dividing an integer after dividing by 2 starting with an integer. So of course we'll end up with just 0 and 1, where again, if we think about it, 0 is what we call the additive identity, and 1 is the multiplicative identity, because again, 0 plus anything is just that thing, and anything times 1 is just the thing itself as well. But this is the wrong translation. Why? Because the actual translation is actually saying that we assume that, in other words, we want to show that or prove that if the first part is true. In other words, if we have the condition that the ring has no zero divisor, we can imply that or prove that this ring is isomorphic to Z2. Well, with the correct translation, it will be a lot easier, and it's actually it turns out to become solvable here, or we can actually prove the conditions to get the results that we have. So how does that work? Here's what we can do. First, we already shown that the ring from part A and part B, that of course with all the elements are idempotents. In other words, the square of the elements will be equal to the elements themselves. We also have the results from part A and part B, which says that 2 times the elements will be equal to 0. Or we can say the element plus itself is equal to 0, as well as having the commutativity in multiplication. We can now just assume that, well, given the ring is has no zero divisor, we can say that well, let's say it's proof. So proof, since we know that the ring has no zero divisor, has no zero divisors, then we can break it into two parts. First, we consider that since it's a ring, it must have the additive identity. In other words, it has 0 in there. So we can assume that first condition that we need to check is, well, 0 times 0 is equal to 0. And again, that is quite trivial, because again, 0 times itself is just a square of it, so it will just giving us back to 0. So this is good. So what we need to check is, now we're trying to make up the subset of this ring here. Let's call it R star, which is actually equal to the ring itself without 0 element. Now, why do you want to do that? Because as we say that R has no 0 divisors, we know that for all the elements in this subset here, we can assume, we also know that has no 0 divisors. No 0 divisors. Then, in this case, we'll say that all elements here in this subset will actually have a condition that no matter what we're going to multiply with, like from this set, we will not be able to get 0 back. Okay. Then what we're going to do is we will try to we have already used A and D problem, so let's call it X here. So suppose let X is actually in this subset, then we of course have the condition that x squared is equal to x based on the fact that x is an element in this subset of the ring, and all these elements will gain the property that x squared is equal to x. Then of course we can just do subtraction here. In other words, we will do the addition with additive inverse here. So in this case, we will just add negative x on both sides to get this. So we get this is equal to 0. Then, of course, we can also do factoring. Again, why? Because once there's no 0 divisors, we can guarantee that not all the elements will guarantee to have multiplicative inverse, but we can guarantee that all the elements are cancelable. In other words, we can do factorization and say that for all the elements here, if we have A times C is equal to B times C, then we can just cancel the C out and conclude that A is equal to B. And this is true for in both directions. Therefore, as we try to factor out this way, we will claim that x times x minus 1 is equal to 0. Then, what are we going to do? Well, we can now try to use the regular algebra and conclude that x is equal to 0 or x minus 1 equal to 0. Of course, it's not actually like that, but what we are trying to say is that now, if we consider it regularly, we will have two parts. But x cannot be equal to 0. First of all, that is because x is belong to this subset that is not including 0. So another way of thinking it is that since x is not equal to 0, where 0 can be considered as x times 0 here. So what does this tell us? This part is telling us from the whole ring itself. And since x is an element that is not 0, by the cancellation property, we can cancel out the x here to conclude that the other parts of the other factor on the left-hand side, which is x minus 1, must be equal to 0. Therefore, as we add 1 on both sides, we conclude that x can only be equal to 1. That means no matter what elements, random elements we try to pick from this subset here that does not include 0, that element must be equal to 1. Therefore, there is only one element in this subset. So in other words, we can conclude that R star is just the subset that contains 1, where 1 again is the multiplicative identity. Now combine it back with this ring, which is actually equal to, again, the ring is equal to this, not just union, but you can see that these two are disjoint. So in other words, we'll have the ring R is equal to 0 and 1. So it only contains 0 and 1, which again is just equal to Z mod 2. And therefore, we just prove the final parts of this problem. As long as we have the condition, or we know that this ring has no 0 divisors, we can prove that this ring is isomorphic to Z2. And that is it. So I hope that you all can enjoy the series of the video that's related to advanced math, such as abstract algebra. And I'll try to make more videos about different topics in advanced math if you guys like it. So if you enjoy these kinds of videos, try to press the like button so that I know how many people will actually want to see these kinds of video again. And also, don't forget to subscribe to my channel so that you can find out more of my other videos, and turn on the notification so that whenever there's a new video, you will not miss it. I'll see you guys in the next video.